look at an example of how do we select materials. Let's go back to a solid. Let's focus on mechanical properties. So you have a stress versus strain diagram. The, in the Hookean region, where stress is linearly proportional to strain, the slope gives the Young's modulus. At a 0.2% offset, which is the case for metals, you can look at where on the stress strain curve a line parallel to this modulus finds a data point of stress, and that's referred to as a yield stress. Then you have an ultimate tensile strength, whereas the stress before failure occurs, the maximum stress. And the stress itself is the force divided by the cross-sectional area, and the strain is change in length by original length. Right? This is the kind of data that comes out from a mechanical property measurement. Let us see how this now translates into material selection. For this, let us build the idea of materials index, and we'll look at what these indices are in the next class to greater detail. But basically, for a design, the performance is limited by either the strength, which is a single material property, and that can be a material index. Sometimes you are interested in modulus over density, and so this is a combination of properties or a materials property group. These are referred to as materials index for the design. So for instance, you have single properties like mass, cost, environmental properties such as embodied energy or carbon dioxide emission. You could also have, for mechanical properties, you could have a stiffness limited design at minimum mass. So you want an E by rho. Okay. So to maximize performance, you take this material index after applying all the constraints and decide whether to maximize it or minimize. Let's see an example. Here is a cylindrical rod, referred to as a tie rod. It has a certain mass, a certain area, certain length, certain density, certain yield strength. Okay. You apply a force in tension, and the length is given, and the maximum load that it should survive is also provided as constraints. Right? So the equation for this constraint is force by A, and that should be less than the yield strength for this part to survive in its function. So let's say the objective is to minimize the mass. Right? So mass is given by AL, okay, where A is the cross-sectional area, so the volume and times the density. Okay. If you substitute for area over here, you will get a performance metric where the mass is defined by the loading condition F, okay, the geometry, which is the length, and this term density divided by the yield strength, rho by sigma y. Okay. To minimize mass, you have to minimize this particular term or maximize its reciprocal, which is the strength per density ratio. So let us see how this is in practice. So you will have a plot of yield strength versus density, and within that, so here is what it looks like, such a plot. Yield strength as a function of density for a number of different materials. The densest materials are metals, the lightest materials are foam. The strongest materials are metals or ceramics, the lightest materials are foams. Right? So how to be able to find out these competing options of something that is light and something that is strong. Right? You will see these groups of properties for families of materials provided in different kinds of shaded regions. Red for metals, yellow for ceramics, about light gray for composites, blue for polymers and elastomers, green for natural materials as a dark green, and this light green for foams. You will also see that there are different kinds of slopes you can apply. In our particular case, we are just looking at the slope of 1. So anything as this gets maximized, if you draw a line parallel to this, you will be able to select, depending upon the yield sigma by rho metric based on L and F, you will see different options that are screened off below the line and different options that are compelling alternatives if they fall above the line. How do these slopes get determined? Let's see an example of it. We took a cylindrical cross section. What happens if you alternatively look at a different cross section? We looked at the applied load as a limiting scenario. What if, instance, stiffness is what we are concerned with? You know from strength of materials that these are all interrelated. So length is specified. Let's say the bending stiffness should be greater than some nominal value. Let's say that is a design constraint. You know from strength of materials that this is related to a constant depending upon the geometry, the modulus, the cross-sectional area, and the length of the material. Right? Cross-sectional area depended upon various parameters over here. Suppose again you want to minimize the mass. Okay. Now, if you go ahead and replace A by rearranging some of these terms, you will come up with this type of a equation where the mass, which is a performance metric that is important in this case, not to be confused with mass of the material itself, depends upon the design constraint in terms of stiffness, depends upon the geometry constant, depends upon the length. So these are all constants based on the specifications. And then you have the option of maximizing E to the power half divided by rho, or minimizing rho divided by E raised to 0.5. So if you choose materials with the largest value of this performance material index, it's the same as the reciprocal of this term. Right. To minimize mass, you increase this material index based on E to the power half divided by rho. How do we come up with this? Using EduPack, which will be the focus of the second module. You have E to the power half divided by rho as the material index. If you take squares on both sides and rearrange term, E will be rho square times m square. If you take logs on both sides, in a plot of E, the modulus, versus rho, the density, you will choose something with a slope of, a line with a slope of 2. Okay. So here's a plot of modulus versus density. And for this kind of a beam, you see that the slope that you have to use is 2. For the tie rod we saw, it turns out that we can derive a similar equation and find out that the slope of this line should be 1. Any option above that line will be viable, anything below will not be so. And it depends upon really the geometry of the loading. right? So something to pay attention to. As we move the ideas forward, in the next class we'll look to greater extent on some of these kinds of tools. In our particular case, we have, based on this derivation, taken a look at that for a beam which is stiffness limited, we look at modulus to the power half divided by density as given by this slope of 2. So in the next class, let's look at some more combinations of property charts by building off from this yield strength versus density that we saw in the case of connecting rods, and also modulus versus density in the case of stiffness limited designs. This will be based on chapter 4.